let me now present the solution to problem G. So as we're given the final state, it makes sense to think about the problems in reverse. So if we look at this final state, there are two things that can happen. Either this was actually the first state or the initial state that we started with, or there was a previous state. Now, if there was a previous state, we can notice that, well, the first thing we can notice is that at each iteration, the encompassing boundary of the cells that are alive always increases by one cell in each of the 4 directions. For example, in the example I gave previously, here we start out with a 2x2 bounding box, which then increases to a 4x4 in the next iteration, and then to a 6x6. We can prove that actually this happens all the time, that there will always be a new cell in each of these new rows and columns that get added to the next bounding box. Yeah, so let's look at this final state that we have here. We know that if this was not this first step, there was a previous step. And in that step, we had a bounding box that was one smaller in all of the directions. So we know that the previous state was completely enclosed in this area here, while now we, for some reason, have some alive cells in the exterior here. In particular, let's consider this top left cell. Let's say it's alive. Now, the only cell adjacent to this cell that was also possibly alive in the previous iteration has to have been in this smaller bounding box, and it turns out this is the only one adjacent to it. So if this one is alive, it means that this one also has to be alive, because if it wasn't, this one would have 0 adjacent alive cells, which means it would have been dead. So if this is alive, this one also has to be alive. Let's now look at this cell here in a similar manner. Let's say this one is dead. Now, the adjacent cells that were also possibly alive in the previous iteration was this cell here that we already know the value of, or the state of, but also now this new cell here. So actually, since this one is dead, and this one here is alive, we know that this one here must also have been alive in order for this new cell to have been dead. So in this way, we can kind of walk through row by row through the smaller bounding box, and basically infer at every step the actual state of the previous, the cells in the previous step. Now, this only works if we never had any errors. So if we didn't have any errors, we can basically go through like this and fill out the complete previous step. And notice that it's completely determined by the current state. However, if we have some errors, we might run into some trouble while doing this backwards tracking here that we have. For example, if we're here at the end, we're filling in this cell here. We will be using this cell here to infer the value of this one. But we can actually go on and check for the last 2 cells here that they actually agree with the state of this cell here. And if it doesn't, we know that there was an error. And we know the error was in this row here, since this failed, since we couldn't infer the value of this based on the cells here above. So if we ever encounter an error in a single row, we know the error must have been somewhere in that row. So the basic idea is we can run this infer procedure down when we hit an error, we know that the error must have been in this row. So in a similar manner, we can also do the same kind of inferring column by column. And if this ever encounters an error, we know that the error was in that in that column. So now we've found both the row and the column where the error occurred, which completely determines which cell it was that got the error. So if there was a cell that had an error, this will tell us which cell it was, in which case we can just flip it. And then basically we just run this infer algorithm again. So in this way we can see that the whole previous state is completely determined from the current state, and we can infer it in this way. Now, since we want the smallest possible initial state that could have resulted in our final state, we basically just apply this as often as we can. We'll apply this basically until we hit an error that we just can't fix in the way that I described. That couldn't have been explained by one single cell being flipped. The bounds on the initial state of the grid says that there are at most 300 rows and columns that contain the alive cells in the initial state. So all of this can be done by straightforward implementation, and it will run in time.